chuẩn, rồi các cái biến thể của BID như thế nào, làm sao để nó chạy và đạt được hiệu quả. Thông thường là chúng ta sẽ sử dụng bộ BID, tuy nhiên là chúng ta rất là ít trường hợp mà chúng ta sử dụng biến thể BID. Và ở đó các cái biến thể BID thì đô hồn nó giải quyết được rất nhiều, rất hiệu quả, rất nhiều bài toán thì chúng ta tiếp tục xem cái phần video này, và cũng như vậy thì chúng ta sẽ hoàn thiện các cái slide hay là keyword về các nội dung ở trong cái phần graphical process control này thì trong này nó khá là nhiều video thì các cái video số 1, số 2 là liên quan tới phần giới thiệu, rồi phần thứ hai cái video số 3, số 4 là liên quan tới cái lý thuyết về hệ thống, và cái video thứ 5, thứ 6 là liên quan tới process behavior, từ 5 tới 8, từ 5 tới 8. Thì thực tế là cái phần này nó sẽ khá là hay, là tương ứng với mỗi cái hệ thống. Ví dụ như là điều khiển áp suất thì nó có những cái đặc trưng như thế nào, điều khiển mức thì nó sẽ có đặc trưng ra sao, rồi tương tự như vậy liên quan tới khí, vân vân. Thì những cái biến động đó thì cái giải pháp điều khiển nào là phù hợp. Thì chúng ta có BID, BPI, thì trong các cái hệ thống đó thì kinh nghiệm của người ta sẽ thấy là liên quan tới đáp ứng như thế này thì cái phần điều khiển nào là hợp lý, chúng ta có thể tối giản một phần, không phải lúc nào chúng ta cũng sử dụng BID. Rồi thì còn hôm nay chúng ta sẽ cũng tiếp tục thử coi cái phần giới thiệu của ông này nó khác biệt gì so với cái thằng hôm trước. Thì hôm trước là chúng ta sẽ đi vào cái phần introduction thôi, nghĩa là cái phần khái niệm về điều khiển process control. Thì thông thường cái phần đó nó sẽ nằm ở cái level của đại học, học đời. Thay vì các cái lớp đó người ta sẽ học về gọi là control theory, thì nó sẽ học về gọi là process control. Cho nên là về cơ bản thì các cái nội dung về điều khiển thì nó sẽ tập trung chủ yếu vào biến đổi Laplace, rồi thì phân tích độ ổn định, vân vân. Còn ở đây thì nó sẽ khác biệt hơn, nghĩa là chúng ta sẽ có khái niệm về điều khiển rồi, và phần thực tế và ứng dụng cho cái phần điều khiển đó như thế nào để làm
in a systematic way, and you'll be able to achieve. Welcome to this video course, Practical Process Control. The aim of this video course is to try to reduce the gap between theory and practice.
Thì cái outcome, cái mục đích của này đó là chúng ta sẽ làm sao để vượt qua cái gap giữa cái lý thuyết và thực tế. Thì những câu outcome này các bạn cũng phải trình bày và đưa vào review the gap between
At the end of this video course, you should be able to run a control system for a simple process.
Thì chúng ta cũng sẽ thiết kế các cái hệ điều khiển cho các cái đối tượng, một số đối tượng thông thường thì chúng ta sẽ có khoảng 8 tuần đầu hay là 9 tuần đầu để mà đi qua hết tất cả các cái bí quyết này, rồi những cái tuần sau, khoảng 5 tuần sau thì chúng ta sẽ thực hành thao tác trên các thiết bị có trên lab, ví dụ có cái bộ về level control hay là temperature controller. Thì trong đó thì chúng ta có thể ứng dụng tất cả các cái phần lý thuyết mà chúng ta học từ giờ cái thực thi, và chúng ta so sánh các kết quả trong bài toán về điều khiển nhiệt độ hay trong bài toán về điều khiển các cái mức
You will be able to understand the process. You'll be able to design a control structure in a systematic way, and you'll be able to tune the underlying controller, either a PID controller or an internal model control. After some real life experience in industry, of course there is nothing that goes above practical experience, you should be able to extend the knowledge that you have acquired in this course to become an expert in designing control systems for complex production lines. Let us have a look at what is on the menu. I will start with an introduction, and the idea is to introduce or reintroduce some basic concepts and notations. We'll also look at the paper production process, and we'll use it to present some of the topics that will be discussed in this video course. In the second section, we will review some system theory. Of course, here the pace will be rather high because this material has been covered in the course Signals and Systems. Some concepts might actually be new to you. For example, the concept of internal stability and the peak sensitivity robustness mode. The next section is dedicated to process behavior. We will start things very simply by considering the gain process, static gain, and we will gradually complexify the process. We will study these processes both in the time and the frequency domain. Knowing the process is knowing its behavior, its interaction with other processes, the type of disturbances that are acting, input and output disturbances, the non-linearities that are present in the process, and constraints. Process knowledge has huge implications on the control structure that will be used and the type of control, PI, PID, internal model control, and so forth. In section 4, we will introduce a systematic way to construct a control structure. We'll do this for a very simple process, but given a bit of experience, you can use this procedure to design process control systems for complex production lines. The main ingredients will be cascade control, feed-forward control, override control, ratio control, split range control, and mid-range control. Section 5 will focus on the PID control. Notice that this section on the PID control comes very late in the course, but this is done on purpose. Before we can tune the controller, we should understand the process and make sure that we have chosen the appropriate control structure, because we cannot compensate an inappropriate control structure by tuning. The focus in this section will lie on understanding the PID controller, and we will propose several tuning methods. We will see that choosing a controller that is not the PI or PID controller comes with certain difficulties and costs. In practice, the PID controller is therefore recycled very often. Typical examples are processes with digital EVs, processes with dead time, with complex responses such as an inverse response, for instance, nonlinear processes, and multivariable processes. This recycling of the PID controller will be the topic of section 6. In big production lines in the paper, steel, food industries, PI and PID controllers are used very often. When they are not used, there's a big, strong possibility that an internal model controller or IMC controller is used. The IMC controller is the topic of section 7. We will construct it from scratch so that you really understand how the controller originates. We will make the link with one of the PID tuning methods of section 5. Section 8 will not be covered in this video course. It applies IMC PID tuning to the DC motor, so you'll find applications for position and speed control in single loop and cascade applications. Section 9 is simply a dictionary with most of the control terminologies in 4 languages: English, French, Dutch, and German. These are the main references that I've used to compile the slides and to compile this video course. I should also thank all the people I've worked with in the 10-year period when I was working at Siemens as a control engineer. These people have learned me quite a lot about control in practice. I also want to mention 2 ACT training courses. The first one, Applied Control Techniques, the second one, Model-Based Control, that I have followed in the early 2000s when I was at Siemens, and these 2 courses have most probably triggered and inspired me to teach in control theory. This is a nice reference because this book can be used without charge to learn about process control. You simply have to click on the link to access the book, and the example of the preheating furnace has been drawn from this reference. I like the 2 references below quite a lot. The first book covers single loop control, and the second book extends the concepts beyond single loop control, as you can see. These 2 books treat process control exclusively in the time domain, and this is perfect for you if you're allergic to the Laplace transform. These books are a good help if you want to discover more and go beyond what you see in this course. Notice that I have borrowed the title of the first book to name this course, Practical Process Control. This is the control system configuration that we'll consider in this course. It's a control system configuration that is very similar to what you have seen in previous courses. For example, the course of Fundamentals of Control Theory of my colleague David Bushel. The output of the controller NV is constructed from the control error. The control error is the set point minus the process value, and over here you can see the feedback part. Here we have the process. We'll assume that there is an actuator. A typical example of an actuator is, for instance, a control valve. Here we have the process dynamics, and of course your controller is acting based on an output that is constructed by a sensor. In the next slide, and very often in this course, we will assume that the actuator effects are included in the process and that the sensor dynamics are flat and 1, so that we can discard the effects. There are of course the disturbances acting on the process. Here, output disturbances, and they will be denoted dV, and there are also load or throughput disturbances, and we'll denote them dL. In the next few slides, we'll put them simply at the input. So the acronyms that you see here vary from one reference to another. For instance, in another reference book we might see different acronyms, and also if you read the documentation that is related to a control system, you might find different acronyms. in reality, the controller has to be implemented on a PLC, on a processor, so it needs to be discretized. What you have to do here is to consider the fact that, well, this signal over here that is analog has to be converted to a digital signal. So you have to take into account quantization, you have to take into account the digital coding. At the output here, the signal is digital, and you have to consider the digital to analog conversion, and very important, the whole mechanism, which is very often a zero-order hold mechanism. In this course, we'll consider a controller that is C of S. Okay? Very often we'll have here some PID control, but this C of S will come from a so-called analog design, right? And in the background, of course, there will be a C of Z that will come from the discretization of this controller. We will assume here that the effects of the zero-order hold mechanism and the other effects related to analog to digital and digital to analog conversions are neglectable. So this means that you can do this for a TS that is small with respect to the main time constant. So this is the hypothesis that we'll take in order for the zero-order hold mechanism not to have too much effect. Another thing that you can say is that you're working with a controller C of S, for instance, a PID. In the background, of course, it's discretized, but you're tuning the PID controller on the actual system. And if you're doing that on the actual system, well, the zero-order hold effects and the effects of the two conversions are automatically taken into account. So this is the control system configuration that we end up with. The process here, it also includes the effects coming from the actuator or the sensor. Here the controller, in our case the controller will very often be a PI or PID control. SP set point is the signal we want to track. PV is the output signal, right? That's the control signal. Over here you see the feedback part. E is the control error, set point minus PV, and on the basis of E, the PID control algorithm will compute in MV. There are two types of disturbances. Disturbances at the output, denoted DV, and load disturbances. Disturbances at the input or disturbances on MV, denoted DL. And with the lowercase letters, you see here acronyms that are sometimes used in the course, or acronyms that refer to acronyms used in previous courses. In practice, there are two important types of control problems: disturbance rejection problems and set point rejection problems. In a disturbance rejection problem, the set point is constant or hardly ever changes. The main goal of the controller is to reject the disturbances, the output disturbances and the load disturbances. Well, a typical example of a disturbance rejection problem is the temperature control of a room. The set point, the temperature set point, hardly ever changes, but the controller has to reject disturbances, for instance due to people coming in and out of the room and disturbances coming from the outside temperature. Set point tracking problems are problems where the controller is designed to follow a reference or set point or trajectories as closely and as fast as possible. So for instance, the closed loop setting time is an important factor. Tracking typically occurs during operating point changes. Just-in-time production plays a more and more important role so that operating point changes occur more often and that set point tracking plays a more important role. People have a tendency to associate the controller with set point tracking, but we'll see that the disturbance rejection capabilities of the controller should not be neglected. Control loop optimization is the art of finding compromises between disturbance rejection performance, tracking performance, but also robustness. Robustness is the sensitivity of the control performance to changes in the process. The control effort or control energy is also of concern, as this control energy is related to the final cost of the product and to wear and lifespan of the actuators. In this course, we will represent a system or a process by the letter P, so we'll use P of S, and in previous courses we might have used HFS because we want to put the focus on the fact that HFS is the Laplace transform of the impulse response. In this course, we'll put the focus on the fact that P here is the process. In the same fashion, we'll use the letter C to denote a controller, although very often the controller that we'll tackle is of course the PID controller. A multivariable vector signal will be denoted in bold, so here y t with the y in bold is a vector signal, whereas y of t without the bold is a scalar signal. Of course, the focus of the course lies on CISO systems, so single input, single output systems. So the process will be denoted by the letter P, as I've said before. At the end of the course, we'll speak a little bit about multivariable systems, so multiple input, multiple output systems, and there the process will be described by a P in bold. There are several control modes associated with the controller, and as I said before, this controller will very often be simply a network PID controller. Well, the first choice that we have is to put this controller in automatic or in manual. In manual mode, the controller output MV is directly manipulated by the operator. And this can be done, for instance, by changing a value MV1 in the human-machine interface to directly influence the process input. In manual mode, the control algorithm, and very often the PID control algorithm, will be used. In automatic mode, the controller output is dictated by the control algorithm, typically, as I said, a PID control algorithm. Well, when switching from manual mode to automatic mode, the control algorithm output might be different from that of the manual. So you have to organize a bumpless transfer from manual to automatic, and this means that the automatic output must track the manual output in manual mode in order to prevent integrated wind-up and also in order to organize this bumpless transfer. We will see this later in the section on integrated wind-up. When in automatic mode, it's a good idea to make sure that this manual value of the man tracks the output of the controller and the auto, so that when you go to manual mode, you have access here to the last available MV in automatic mode. This will ensure a bumpless transfer, and if needed, the operator can choose to change the value in the mode. The second control mode has to do with the setpoint. So this control can either be in external setpoint mode or in internal setpoint mode. Sometimes you find other names such as remote setpoint and local setpoint. So external setpoint mode corresponds to remote setpoint mode, and internal setpoint mode corresponds to local setpoint mode. In external mode, we speak about an external set point. This means that the set point of the controller comes from a remote location, from something that is external to the system. For instance, a data bank or the output of another controller, and this is the case, for instance, in a cascade. In internal mode, we speak about an internal set point or a local set point. The operator sets the set point of the controller directly through the human-machine interface. Again, there might be problems when switching from one mode to another, so for instance from external set point mode to internal set point mode. We have to organize a dump list transfer from external to internal set point. So when you're in external set point mode, the internal set point must follow the external set point, so that when we go to internal mode, well, the internal set point coincides with the last external set point. There might also be problems when switching from internal set point mode to external set point mode, for instance in a cascade. When in internal mode, the external set point should be chosen appropriately, and this will be discussed in the section on cascade control. The third control mode is the output tracking mode or interrupt mode. When this binary signal here, track on, is set to 1, then the controller output MV will track the value here, track value. This is a signal that can be chosen by the one that is programming the control algorithm. When track on is set to 1, the control algorithm is inactive, and as I said, MV is equal to track value. I said that the control algorithm is inactive, but this has to be done in the proper way in order to prevent integrator windup. We will see this later in the section devoted to integrator windup, in which we implement a controller that has this output tracking mode or interrupt mode. An example of output tracking is the following. Assume here that there is a measurement PV that comes from a sensor, and that this sensor provides a binary flag to tell you if the measurement is okay or not. So if PV not here is 1, this means that the measurement is not valid. Well, if this sensor is giving you this flag, PV not is equal to 1, this means that the process value measurement is no longer valid, and of course you cannot use it for control. So what you should do is freeze the controller. This can be done as follows. You connect the PV knock signal flag coming from the sensor to track on, and you connect MV, the output of the controller, to track value. What will happen when the sensor flags a signal measurement that is wrong? Well, this one will go to 1, and MV will track itself, so that you have here at the output the last value that you have in automatic mode. Okay, so the controller is frozen with the last active value of MV. The controller is locked, and of course in the human-machine interface there should be a warning for the operator to tell him that there is something wrong with the measurement, but at least nothing goes wrong in the sense that the controller is now locked. There are many reasons why a controller can be locked, so usually there will not be one track on binary signal, but several of them. So there will be several track on binary signals with corresponding track value. Track number 1, for instance, has priority over track number 2, which has priority over track number 3. So if several of the track on are set to 1, MV will follow the activated track bar I with the highest priority. Usually, the reason why a controller is locked is displayed in the faceplate of the controller in the human-machine interface. As you can see over here, trackval is equal to NV, but this is only one of the many possibilities, as you will see later in the course when we consider cascade control and output tracking in that applicable case. I will now introduce the Siemens SIMATIC PCS7 system. You will find more information about it on the net, and this PCS7 BCS system can be used to automate one or several large production lines. What I will do is use a version 8, so a slightly older version than the version 9 that is now available, to illustrate some of the concepts of the course. I will start by illustrating the different control modes that I've just talked about. What you see over here is the SIMATIC Manager. It allows you to interact with the PCS7 system, with the actual process, with the controller, and with the human-machine interface. What we will do here is use a 7PLC sim to actually emulate a PLC. What we'll do is kind of program or model the system and design a controller for it and a human-machine interface in Siemens Windows Control Center. I will now briefly show you what the different components are of the SIMATIC Manager. Well, first of all, what you can do is introduce the hardware configuration. So you have to choose CPU, right? Here we're working in simulation, so I've just added a CPU. In reality, of course, you'll have to interact with the system, so there might be several CPUs, and of course there will be I/O, so you'll have to choose some of these cards: analog input cards, analog output cards, digital in and digital output cards. Once you have done this properly and that you have compiled things and downloaded to the relevant CPUs, well, you can interact with the actual system. In this section, you will find everything that has to do with the programming. Here is the source container. If you have a look, for instance, you will find over here the source code to implement a lead lag system using SCL code. This is a Siemens language called Structured Coded Language. We'll come back to that later in the section dedicated to process behavior. Over here we have the block container with the FBs, so function blocks. We have an instance DBs, FCs, just functions, and then DBs, data blocks. This looks very similar to what you've seen in other courses, but probably on a system coming from another vendor. What you will see over here is the function block lead lag that will implement the lead lag system, and it has resulted from the compilation of the code that I just showed you before. Here you have the CFC chart folder. CFC stands for Continuous Function Charts, and CFC is a graph editor that allows you to program the entire control software. Let us open a few charts. What you see over here is a chart that allows you to implement a process. Remember here that we use PLC sim, so we do not have any actual system. So what we'll do is simulate the system, emulate the system, and you can see that we can do this very easily using this graphical editor. So this is a dead time, and this is this lead lag block FB3 that has resulted from the compilation of the SCL code that I've shown you. As you can see over here, we can construct a simulated process using a dead time, several lead lag systems, a resonant block, and some noise. These blocks are running with a certain sampling interval, but we'll come back to that later. We can have a quick look at the PID controller just to give you an idea of the type of block that is used in PCS7. It's much more than a block with simply a few inputs and a few outputs, but this will become clear later in this course. Once the program has been compiled and downloaded, I will not do it right now, you can interact with the system directly in CFC and see the different variables. So for instance, this is my lead lag system, and here you see the input and the output. Instead of interacting with the system using CFC, what you can do is also design your human-machine interface. And for Siemens, this is done using WinCC, so the Windows Control Center. So what you can do is compile everything so that the variables become available in the WinCC Control Center. And what you can then do is design pictures of the type that you see over here to generate a nice human-machine interface. So we will stop this because this will take too much time. We can have a look at one of these images, for instance this one. Or here you can design your interface with the actual system, so the human-machine interface. Here it seems it's done using the graphics designer that is associated to the Windows Control Center WinCC. Very often what is done is that there is a drawing of the PID so that the operator can see where he is interacting with the system, and usually faceplates are used, I will show you later, to interact, for instance, with the PID controls. There are curves and there are possibilities to interact with certain parameters. And if I go and have a look at the properties of this one, you will see here that there is a link with a variable that has been obtained using this compilation procedure. This is how you make the link with what is happening in the actual PLC. So this is how it looks like in real life in the human-machine interface. So here, Windows Control Center. This is for the preheater example that we will treat later on in the course, so I will not go too much in the details, but you can see here the trends. You can interact with the system, so I can, for instance, change the set points. So you can see that the set point is decreasing here. There is a ramp on the set point, so it does not decrease directly, but you will see that it will stabilize at 60, and you can have a look at the parameters. We will not go into the details of this system for the moment. This is for later. What I want to illustrate are the controller modes that we have talked about previously. So this is the WinCC interface with the process that we have programmed. So in this way we can change the emulated process. In this case it has a dead time of 2 seconds. There are two first order systems that you can see, because here the lead time constants are 0. We'll come back to that later. The first order system has a time constant of 10 seconds and the second one of 3 seconds, and we have added some noise. Here we can interact with the process, with the controller using this interface, and as you can see here, this controller is in automatic mode and internal set point. So this means that since we are in internal set point, the operator, in this case we, can change the set point locally. So we can change the set point to 60% or percent degrees here, because it's a temperature controller. As you can see here in blue you have the set point, in green the process value, and here in brown the output of the controller. So what you can do also to illustrate here the concept of automatic and manual mode is go to manual mode. Observe here that the manipulated value NV is fluctuating. When the controller will go to manual mode, the last active value in automatic mode will be selected and will have a bumpless transfer. This is illustrated now. As you can see, the value is fixed to its last automatic value. I am in manual mode and I can change the manual value. So now I'm interacting directly with the process because I am imposing the input of the process. So I have just changed the manual value to 40%. And as you can see, the system is interacting with that. So I hope with this that you see the difference between automatic mode and manual mode. Well, in order to illustrate the concepts of internal mode and external mode and output tracking, I'm going to use another system here, and it's a cascade system. I will not go too much into the details because this process will be used when I will be talking about cascade control. But it suffices to say here that you have an outer loop and an inner loop, or a master loop here and a slave loop. Okay, so the master loop is controlling the temperature over here, and it is setting the flow of fuel here. And the fuel flow is controlled using this slave control by acting on the control valve over here. So let's open the two control faceplates. So as you can see here, I have the master and here I have the slave, right? And you can see here that the slave controller is in external mode. It is impossible to change by clicking over here the set point of this controller, because this slave controller receives the set point from the master controller. You can see it over here. The manipulated value of the master controller is the set point of the slave controller. So what we can do now is change and go to internal set point mode, and you will see here that the set point will change color, and it is also possible now to go, for instance, to a set point of 5 liters per minute. Okay, so we are in internal set point. So this means now that the link between the manipulated value of this controller and the set point of this controller has been broken. Okay, we will see when we talk about cascade control that you have to do something about this controller. If you do nothing, you will see that there will be a wind up of the integral action. So what you will have to do is make sure that this controller goes into tracking mode or input lock mode, and you can see that it has done this. You can see here tracking mode and the T appearing here. Okay, so the PID control algorithm has become inactive, and the output of the controller is actually, in this case here, the process value of this. We will see this later. You can see here that the manipulated value is now tracking the process value, and this one is in tracking mode. If I go to external mode again, this controller will be acting again, will be controller, and you will see here that this tracking will be disappearing. Again, here we have this cascade control that is active, and what you see over here is indeed again the set point. Well, using this faceplate that you've seen before, it is possible to interact with the PID controller, here a temperature PID controller. There are similar faceplates for control valves and for actuators. If we click on the faceplate, this is what you obtain. In this part we have already seen, but you can also, of course, change the control parameters. Okay, so the parameters of the PID, so this is the PID control gain, the integral time constant, and the derivative time constant. We'll come back to that later. You can also set limits, right? And if PV goes outside these limits, an alarm is generated. Here all limits have been deactivated except a warning and an alarm on the maximum value of PV. As you can see now, the process value is at 60. So if we, for instance, put a warning level of 40 degrees, we should obtain alarm. As you can see over here, it's clearly shown that the PV of this controller has exceeded the warning limit. Assume now that the operator is looking at some other part of the process. It is clear from this warning that there is a problem, and he can click and see where the problem is coming from. Of course, then he has to do something about this problem. For us, it's rather easy. We put the old value and the problem is solved. In reality, of course, things will become a little bit more difficult, and then you can quit the app. It is possible to consult the list of previous alarms, and this is what you obtain. Of course, here there is only one type of alarm, but you can see that this high warning limit violation has occurred several times. The last time that it has occurred, it was active for 35 seconds, and it was quitted after 43 seconds. The process and instrumentation diagram is a very important diagram in which you find a lot of information that is important to you as a control engineer. Sometimes instead of the name process, you'll find piping, and instead of diagram, you'll find draw. Well, this is a definition of the PID that I've drawn from Wikipedia. The PID is a diagram which shows the interconnection of process equipment and the instrumentation used to control the process. In the process industry, a standard set of symbols, and we'll talk about that later, is used to prepare drawings of processes. The instrument symbols used in these drawings are generally based on the ISA standard S5.1. ISA stands for International Society of Automation. The PNIDs are used for laying out a process control installation, so they're very important in the design phase. They play a significant role in the maintenance and modification management of the process, but also of the controller structure that it describes. And the PNIDs form the basis of the live mimic diagrams displayed on graphical user interfaces of large industrial control systems. And we have just seen this on the SCADA system WinCC in the example of the preheater. Here SCADA stands for Supervisory Control and Data Acquisition. It goes without saying that these PNIDs should always keep up to date. Here is a list of items that you can find in a PNID. You'll have information about the instrumentation, so the sensor, the type of transducer, the type of analog electrical signal, mechanical equipment with names and numbers, all valves with their identifications, process piping, sizes and identification, flow directions of material, and of course, very important for us control engineers, the control structure. So the control inputs, outputs, interlocks, feed forward, cascades, and things like that. Well, you should use the correct ISA identification and reference designations. Typically, for measurements within a process, the first letter relates to the type of measurement, so F for flow, L for level, P for pressure, and so on. The subsequent letters will have to do with the type of device. Is it a controller, a control valve, and so on. So here we have a few examples. FC stands for flow controller, FT for flow transmitter, FCV for flow control valve. You should use the correct ISA symbols for the equipment. So here are a few examples. This is the symbol for a control valve, a manual valve, and so on. So please refer to the ISA standard S5.1, and there is also software available with libraries that will make it easy for you to select the correct equipment symbols and to draw nice PNID diagrams. Well, here's an example that comes from the water level control of a steam boiler. You can see here that there are parts of the control structure, and here there are two measurements. You can see here that this is really a PT stands for pressure transmitter, so this is a pressure measurement, and over here you see here LT, so this is a level measurement. You will see that the representations of a PID controller in a PNID and in this course are often simplified. So this is the PID controller as you know it, represented as you know it. So here it's acting on a pulp. So it's based on, the PV is a level measurement, as you can see, because we have a measurement coming from a level transmitter. Inside the control error is constructed, so the level set point minus the level measurement, right? And based on this error, the output of the controller is constructed, the manipulated value that will be used to control the opening of the control valve. We'll come back to this particular process a little bit later. What we'll often do is simplify this representation as follows. Very often this will be the representation that we will use, and this means that we are using a level measurement to control the system using this control valve. So behind this simplified representation, you have to kind of imagine the level transmitter, the level set point, and the actual PID controller. Before talking about the paper machine example, I will show you a short video about the paper process. So the video that you're about to see is based on the references that you see here on the screen. The different parts described in the video, the pulper, the wire section, etc., well, they come from different machines. Very often also old technology is shown, for instance at the wire section, but showing old technology has the advantage that it's easier to see things and easier to explain things.
Other products come partly from the items in your recycling bin, but also from schools, office buildings, printing shops, and other industries. This is what we call the urban forest. Everything you put in your recycling bin ends up at the sorting plant. Paper and cardboard is compressed and tied into bundles to make them easier to transport.
The delicate paper web is now uploaded into the press section by continuously looped wet felts, which carry away most of the water and stop the sheet from tearing. The longer section of the paper machine contains the drying cylinders. These huge heated rollers dry the paper, giving it the strength to become self-supporting, ready for the processes which will determine its surface qualities.
We'll now go over the different control loops in the paper machine example. You will see that controlling the paper process requires quite a bit of classical process control know-how, and we'll be able to make links with almost all of the control structures and controllers covered in this course. We assume here that the paper process is based on recovered paper bills. The paper bills are brought inside the paper using a transporter or conveyor belt. In the paper is shredded into pieces, as we've seen in the video. The water is added and the paper dissolves, and the pulp, sometimes called stock, is formed. The main parameter or measurement that is associated with pulp is consistency. Consistency is the ratio of dry fiber content weight over total weight expressed in percent. This consistency tells you how thick the pulp is and how much fibers it contains. Let us have a look at the level control that you see here in blue. The level of the controller is adjusted using the control valve, which itself is used to adapt the water flow inside the paper. Here it is very important to meet the level set point as close as possible. The process from control valve to level is an integrating process, and we'll see that a PI controller needs to be used over here. This is covered in section 6 about level control. So the consistency control loop is shown in red. The consistency of the pulp is measured using this transmitter and controlled by adapting the speed of the conveyor belt. In some cases, the speed of this conveyor belt is fixed, and the conveyor belt is either running or it is not running, and then you're in the off state. And what the controller should provide is the on-off sequence to the conveyor belt. This type of control will require PWM, pulse width modulation. This should ring a bell because this is a concept that we've seen in other courses. And this type of control is covered in section 6 on digital MVs. The probe then leaves the paper to go through centrifugal cleaners, also called cyclones. The heavy parts are removed from the stock. The probe also goes through several stages of filtering and screening, but this is not shown on the picture. What is important to understand is that these centrifugal cleaners, those cyclones, will operate at their best when the stock flow is not changing too abruptly. So what has to be avoided is the step-like flow changes through the cyclones. Well, we arrive now at the next control loop, shown in orange over here, and this is the level control in this tank. The level is controlled using this pump. This level controller will be quite different to the level controller that we have seen over here. Here the level has to be maintained on set point in a very strict way. So what we'll see here at the output of this tank is that when a machine starts, since there is a sudden step-like demand of torque flow. So the output will look like this. So now imagine that we have a controller implemented here that is of the type implemented over here. So a controller that will maintain the level in the tank very strictly. Well, this step-like demand at the output will propagate to a step-like demand at the input, okay? But remember that your cyclones will operate best when you do not have any sudden flow changes, okay? So this is not something that we design. We would like to see something that is smoothed over a longer period, something like this, right? So that this change is propagated over a longer period, and you do not have these sudden stop flow changes through the cleaning stages. One way to achieve this is to use this tank here as a buffer tank. So the idea is that you allow the level to deviate from the level set point for a little while. So this can be achieved by implementing a so-called non-linear PI controller, and this will be tackled in section 6 again on level control. The torque or stop is then pumped from the buffer tank to the headbox. The purpose of this headbox is to deliver the torque through a lip so that a stop flow jet is formed that falls onto the screen, onto the wire section. There the paper web is formed, and as you've seen in the video, the water is removed first by gravitation and then subsequently by vacuum using suction boxes. At the end of the wire section, the paper web enters the press section, where the water content in the paper web is further decreased by pressing the paper in between two fans. Well, next the paper web enters the dryer or dry section, and the paper runs on steam heated cylinders to evaporate the remaining moisture content. The temperature of the cylinders is controlled using the steam pressure. At the exit of the dry section, the web is scanned and the relevant quality parameters are obtained: grammage in gram per square meter and moisture content in percent. Subsequently, the paper is winded on a wheel. The grammage of the paper web is controlled by adapting the stock flow, as you can see over here. Now the distance between the headbox, and this is where you're influencing the grammage, and the place where you're measuring grammage, so that's at the scanner. Well, this distance is approximately, let's say, 500 meters, okay? So there is a huge dead time with respect to the main time constants of the process. This calls for specialized control methods. One option is to use a SNC predictor, and this is covered in section 6, or you can use also an internal model controller, and this is covered in section 7. In this type of control, well, usually an internal model controller is used. Depending on the grammage of the paper web, the speed of the production line needs to be adapted. A high grammage will result in a lower speed. This makes sense. The paper web has to spend more time when it's heavier in the dry section as there is more moisture to evaporate. Now, if the production speed changes, this means that the delay we call it dt over here, will change because it is this distance that has to be covered divided by the speed. So you have units meters divided by meters per second, and you'll have something in seconds. So if the production speed is changing, the dead time is changing. You can see that the process dynamics will change with the operating point. In this case, the operating point is dictated by the production speed. If the process dynamics changes, this means that the controller, the internal model controller, should change as well. And this is achieved by doing scheduling. And this is covered in section 6. The grammage controller is affected by the speed of the production line and the consistency of the stock. An increase of the production line will require a higher stock flow, and an increase in the consistency of the stock will require a lower or a decrease in the stock flow. When the stock is thicker, contains more fibers, you require less stock flow to obtain the same grammage. Let us consider a stock consistency change. We can do two things. First thing that we could do is wait until the effect of the consistency change has produced a change in the grammage, and then your controller will read. This is the reactive way, and it will be slow. What you could do instead is act immediately as soon as you sense the consistency change and adapt the stock flow accordingly, and this is the proactive way. If you do things correctly, you might even not see a change in the grammage. But here, since the two disturbances, the consistency of the stock and speed are available for measurement, they can be used for feed forward, right? And this is covered in section 4. In this drawing, it looks as if the internal model controller is directly interacting with the pump. In reality here, you have a flow transmitter, and you have also a local stock flow control loop. Okay, so what is happening is that you have an internal model control. This is the master. It sets the stock flow set point, and this local loop is implementing this stock flow control. The advantage is that when there is a pressure drop in this line over here, this pressure drop will of course affect the stock flow, and this will be immediately picked up by this flow transmitter, and this local stock flow loop will reject this load disturbance. This is a cascade, and cascade control is covered in section 4. The moisture content of the paperwork is influenced by both the production line speed and the steam pressure in the cylinders. Well, depending on the grammage that is produced, the strategy will be different. For low grammages, the limiting factor is the production speed. So the production will be at maximum speed, and the moisture content will be controlled by adapting the steam pressure of the cylinder, and this is what is shown over here. Now for high grammages, the
limiting factor will be the drying capacity of the production line. So the production will be done at maximum drying capacity. So we set all steam pressures at their maximum value, and we control moisture using speed, as is shown here on the screen. Well, in this paper process, there are also coupling effects between moisture and grammage. For instance, if you control moisture using speed, this is when the drying capacity is limited, as we are seeing. Well, you can see that the grammage is also influenced by this speed change. But in this case, since we have implemented a feed forwards, well, this coupling effects will be mitigated by this feed forward. When the grammage is adapted using a change in stock flow, as shown over here, well, this stock flow change has also an influence on the moisture content. So there is kind of an interaction, a coupling effect, and these coupling effects are not desired because they could cause the grammage and moisture control to fight each other. We need decoupling, and this is discussed in section 6. As you have seen in the video, the dryer section is covered by a hood to minimize energy losses. Well, the airflow through the hood, as you can see over here, has to be controlled, and the airflow setpoint is really critical. If you play it safe and you set this airflow setpoint too high, of course you will have too much energy losses. If you set it too low, the so-called dew points, and rosé in French, can be reached in the hood, and the water vapor will condense in small droplets, causing paper breaks. The idea is to control as close as possible to the dew point without reaching it. Process control can be represented as a hierarchy. Level 1 corresponds to base layer control. This level is also sometimes called the field level. These are the devices, sensors, actuators, proximity switches, on-off valves, and so on that you can see in the field. The control that is associated is typically sequential in nature. Level 2 is the safety level. It involves environment and equipment protection. Safety instrumented control systems, so for example safety PLCs, that are physically separated from the general purpose control system, monitor the system and intervene when dangerous situations arise. Level 3 is the level that will be considered in this course. It involves process control for single loop systems and multivariable systems. The control will often be a PID control or a model-based controller, a simple model-based controller such as an internal model controller. The controller is often associated with a control structure that will involve, for instance, feed-forward cascade control and so on. Level 4 implements more advanced types of control that involve real-time optimization. One such method is model predictive control, and students in control engineering have encountered this technique in the course of my colleague Thomas Muser. The next level is the planning level. This level uses a computer-based management system called Manufacturing Execution System, or MES. This system monitors the plant from raw materials to finished goods so that management can plan, schedule the production. On top of this, you might sometimes find a management level which uses an enterprise resource planning system, or ERP system, for operational management at enterprise level.
The control hierarchy is often represented as a pyramid, as you can see over here. From bottom to top, you will see that time scales evolve from a second or less at the field level to several days or months at the top planning and scheduling level. Similarly, you will see that the spatial scale will evolve from something that is very local, for instance a unit part in the field level, to a production or even several production lines in the planning and scheduling level 5. In process control, the choice of the set point is very important. Let us take the example of the choice of the set point for the airflow that goes through the hood. If it is not chosen properly, well, this could lead to condensation in the hood, and this will of course cause economical loss. Well, variations around the set point and well, the speed at which PV goes to set point when you do a change of set point are very important. As I said, to prevent economical loss, for instance, if you're producing an 80 gram per square meter paper and you want to produce now 100 gram per square meter paper, well, this transition from one set point, from one product to another should be as short as possible, because the product that is in between these 80 grams per square meters and 100 grams per square meter cannot be sold, so it corresponds to economical loss. Going to the set point as fast as possible is therefore very important. Well, variations around the set point must also be kept under control for security reasons, safety reasons. Think of pressure in a boiler or the level in a tank. Keeping the process value PV around the set point SP will also maintain the process around a working part, and this might minimize the effects of non-linearities. Another reason to minimize the variations around the set point is that when you decrease the variance around the set point, well, you can actually very often shift the set point itself. This is the very well-known algorithm: decrease the variance and shift the mean. This will be explored in the next slide. While minimizing the variations of PV around the set point, you should always look at the cost, and the cost is of course in terms of the control energy. This means that you should look at your set point PV, but also look at the manipulated value. This is sometimes forgotten, and this is sometimes even forgotten in control reference groups. There are of course quite a few challenges associated with process control. Some PVs are not available for measurement because of the cost of the sensor, or because technology does not offer a sensing solution. Sometimes soft sensors, for instance observer-based sensor, can offer a solution, and this should be a plan for control engineering students, as we have tackled this in the course of state space control. Sometimes the signals are noisy, so filtering offers a solution, or sometimes the sensors are badly located, so they will produce a dead time. So you should always look at the location of the sensors during the process design phase. Sometimes there will be several influences on the PV that you want to control, so you have to choose the correct influence for the appropriate engineer, and you have to mitigate the effects of the other influences using decoupling and or feed forward. Sometimes the control problem becomes challenging because of the involved open loop dynamics, so you have to tackle difficult dynamics. First example is if this is step at the input in open loop and you have a large dead time with a small time constant, well, this ratio here, dead time over time constant, will make the problem challenging if this dead time becomes large with respect to the time constant. And of course, if you have an inverse response, this is something that looks like this. Well, this will of course make things even worse, and inverse responses are linked to the zeros that are to the right of the imaginary axis in the Lorentz theorem. Sometimes the process is difficult to understand, and one reason for that could be that the process is simply non-linear. This will result in different dynamics around different operating points. We have already seen an example of that in the paper process, or the relation, the dynamics that goes from structure to damage changes according to the operating point. The operating point is dictated by the speed of the line. We had seen that the delay in the system was operating point dependent. Well, let us now look at this paradigm, decrease the variance shift domain. This paradigm is often used to improve the economics of the process, and it's one of the important topics of this course. Most production processes have tolerances on the process variable. It might be a lower tolerance or an upper tolerance. Here in this case it's an upper tolerance, and it will correct tolerance plus. Let us take an example again in the paper industry. The paper producer is selling his paper reels to an end customer, and the end customer will say, well, the upper limit on the moisture content is 8%. If you go above that upper tolerance, you can take your paper reels out. And this is the economical loss for the paper producer. So the paper producer has to make sure that PV stays below the upper tolerance, and you can do that by selecting the set point in his moisture control. So how will he do that? He will look at PV, previous PVs coming from the past, and he will look at the 3 sigma value, and he will set its set point as follows. It will be the upper tolerance for purpose minus 3 times the sigma on PV. He has had a course on statistics in the past, and he knows that in 99% of the cases the PV will remain below the upper tolerances if the production process is running in a normal fashion. Well, as this animation shows, if the paper producer manages to control through better disturbance rejection to decrease the variance of PV around the set point, he will be able to shift the set point so that it becomes closer to the upper tolerance. Well, you can clearly see that the variations around the set point are clearly smaller in this second situation. This means that the standard deviation has been decreased through control, and this means that the associated set point that can be chosen, remember that it is the upper tolerance minus 3 times sigma 2, is not much higher. The application of this paradigm has allowed us to decrease the variance or the standard deviation of the moisture content, and this has allowed us to shift the moisture content set point. In this case, well, we have been increasing it. Well, assume that you control the moisture content using the speed of the correction line. Since you have a higher moisture content set point, well, you can go through the dry section faster, and this will lead to a production increase, right? Assume that you're controlling the moisture content using the steam pressure. Well, a higher moisture content set point will lead to lower steam pressure set points. So in terms of energy savings, this is really also advantage. So you can see here that using this paradigm can be used to improve the economics of the process. And well, decreasing the variance is a really disturbance rejection. So disturbance rejection is really an important component of control. People have often the tendency to think that set point tracking is very important and forget about disturbance rejection. You can also see this in terms of the frequency or probability distribution. This line corresponds to PV average. If your controller ensures a zero steady state error, this will correspond to the set point. So by ensuring that this point here, set point plus 3 times sigma on PV corresponds to the upper tolerance, well, you make sure that the probability that the actual PV will be in the interval set point plus 3 times standard deviation on PV and set point minus 3 times sigma on PV is approximately 0.997. So you have a probability that is very near to 100% that your actual PV will stay below the upper tolerance. And by decreasing the standard deviation, well, you can increase the set point, you can shift the mean. In summary, once the disturbance rejection has improved so that the variance or the standard deviation has increased, the controller set point can be adapted, the mean can be shifted to improve the economics. Depending on the control problem, the set point is either increased or decreased. In the moisture control problem, the moisture set point could be increased, and this led to an increase in production if moisture was controlled using light speed, the production on light speed. Notice also that there is more water content in the end product, and often these paper wheels are sold by the weight, so this is another advantage. Well, let us take an example where the set point is decreased, and such an example comes from the production of beverage packing material. So what you have is board, right? So this is board, carton in French. And what is done is that a layer of polyethylene is extruded on this board, and then there is a layer of aluminum, right? And what happens is that the end customer that buys this beverage packaging material imposes a lower tolerance on this polyethylene layer, and again it's expressed for instance in grams per square meter, right? So the one that is producing this beverage packaging material will choose the set point as follows. He will say, well, I'll take the minimum tolerance and I'll add now 3 times the standard deviation that I see on my measurement of PE. So if the producer, through a better disturbance rejection, can decrease sigma, you can see that the set point here, using this formula, will be decreased. So this method is sometimes called set point optimization, and the idea is to keep the set point as close as possible to the upper or lower tolerances depending on the type of control problem. And in the computation over here, we'll either have an upper or a lower tolerance with the associated sign, and X here is the confidence level. In the previous example, we had X is equal to 3, so the associated probabilities were 99.7%. In the previous example, sigma, the standard deviation, was computed by considering previous data sets of PV. You compute the standard deviation and then you obtain the set point so that the set point was fixed. But you can actually monitor the standard deviation in a continuous fashion. Okay, what you could do is, for instance, compute a moving standard deviation over a fixed number of samples. And what will happen is that sigma will change so that you can continuously adapt the sample. Of course, if you do such a thing, well, you have to implement measures so that this computation of the optimal set points can be done in a safe fashion. For instance, that there is a maximum and minimum value and that there is some gradient that is imposed. There are, of course, a number of benefits when you compare process control in automatic mode to manual control. The speed and frequency of action is better. So every sampling instant you have a new NV that is computed, so the variations in NV will be smaller and also the deviations from set point will be smaller. Well, the control action is based on a PID algorithm so that you take quantitative decisions and they will always be the same under the same circumstances. Of course, you can run several controllers in your PLC so that you can do simultaneous variable changes, whereas an operator is of course limited in the number of controllers or processes that you can monitor. The consequences of process control in automatic mode is that the operator becomes a supervisor and that the productivity will improve and go together with more consistent product quality properties. Well, there is also a big chance that there is a reduction in the energy consumption and an increase in the operation safety. And since when you do process control, you have to do it on the basis of model very often, you will improve your understanding of the process. You might wonder why we are comparing process control in automatic mode with process control in manual mode. Well, even in a modern control system, manual mode might be encountered often. Manual mode, except in certain situations such as production startup, is often indicative of a problematic situation. For example, a control that is not tuned properly, a control structure that is not adequate. And what happens is that the operator does not have confidence in the control action and takes the controller to manual mode. These are the desirable features for regulatory control. Well, the first feature is not desirable, it is necessary. We have to impose the stability of the closed loop system. The second feature has to do with tracking. We want PV to go to its set point as fast as possible. So when there is a closed loop set point change, well, you have indices like settling time, rise time, and so on. Of course, you have to have an adequate disturbance rejection, and this you can see in terms of variation around the set point. You have to be insensitive to model and measurement noise. So this means that if the process, for instance, changes a bit, well, the process controller should still be able to control the system with adequate performance. And this is sometimes called robustness. It is, of course, important to meet these indices without having an excessive controller action NV. And well, it is important if the process is non-linear that you meet these performance indices over a wide range of operating conditions. In practice, it is in most cases impossible to satisfy all 6 features, so you have to look for a trade-off. Well, besides stabilizing the system, well, process control can achieve quite a lot of things. You can keep the process at the prescribed target. This is set-point tracking. You can simplify transitions from one operating point to another. You can reject perturbations, so input load disturbances or output disturbances. You can robustify the system. You can make sure that the controller finds the optimum operating point. You can enhance process analysis and improve your process know-how. You can improve safety, security, extend the life of your equipment, improve process operability, and improve economics. Modern-day digital control systems can handle thousands of variables in an accurate fashion. Everything happens in a decentralized way, in the sense that the analog to digital conversion is done locally, and then the information is communicated to the central PLC using a bus system. These systems have similar conditioning capabilities, so for instance noise removal and filtering, but also calibration possibilities of the different measurements. You can easily interact with the system using the HMI or supervisory control and data acquisition system, SCADA system. In the case of Siemens, well, it is the Windows control system WinCC. You can interact with the system through faceplates for motors, valves, controllers, and the alarms pop up and they make it easy for you to locate the problem or the interlock. The alarms come with occurrence statistics so that you can do a Pareto analysis. If you tackle 20% of the most frequent alarms, you can correct 80% of the underlying problems. There's a management information system, capabilities for reporting and trending, computation of statistics in the time and frequency. So for instance, you could associate with each reel of data that is produced a report that gives you the indices, the quality indices, for instance grammage and moisture over the production time of the reel, with statistics as average, standard deviation, and so on. The most modern control systems integrate all levels of control from the process control pyramid that we've seen earlier, from basis layer control to the planning and scheduling level. These systems will also give you remote access and diagnostics, which is interesting if you have just commissioned a production line in a faraway country and you've just come home. You can still interact with the process control system. Some of those systems will even propose tools for control performance monitoring. Each control loop will be evaluated in terms of tracking and disturbance rejection performance using key performance indicators. In this way, you can easily isolate the problematic control loops and you know where to concentrate the tuning effort. Some of these systems will even propose new tuning parameters. The objective of feedback is to cope effectively with change. There are three main sources of change. The first one are disturbances. These disturbances can act at the input, then we speak of a load disturbance, or they can act at the output, and you have here a list of typical disturbances. A second source of change is a set point change, and this is of course initiated by the operator, or we can have a transition between set points, and then we speak of a tracking of a desirable path. The third source of change is a change of operating point, and this source of change is often forgotten. It comes from the non-linearity of the process. If you change operating point, well, you have a change in the dynamics. Well, feedback control will also help you to cope with change in the process. Well, the Bode diagram of the loop gain, and this is a reminder from the course of Fundamentals of Control Theory and the course maybe of Digital Control. For the Bode diagram of the loop gain is PC, looks something like this. We have here the crossover frequency. You have a zone where the slope is around minus 20 degrees per decade. Then in the low frequencies you have a high loop gain, probably because you have put an integrator in the controller, and then you have a high range. So this is your crossover frequency, right? Well, the transfer function from set point to PV is PC over 1 plus PC. And since at the low frequencies you have a high loop gain, well, in those frequencies this transfer function will be approximately 1 because of this high loop gain. And you can see here that variations of P will be mitigated by the feedback principle. Right? The transfer function from TV output disturbance to TV is 1 over 1 plus PC, and you can see here that in those frequency ranges, right, well, this transfer function will change to 0, so you'll be attenuating the disturbances dV. And again here, if P is varying, if you have changes in the process, this will be mitigated by the fact that you have here a high loop gain, and feedback will again cope with this change in the process. There are essentially 3 approaches to feedback. The first one is the model-free approach. The control action is based on current and past information and tuning constants, but the process description is never used in the control algorithm itself. A good example of that is, of course, the PID controller. It is a fixed control algorithm in which the process description is not used. Of course, what could be done is that you use your knowledge of the process to tune the PID controller, but the process description is not used in the control algorithm itself. The second approach is a model-based approach, but the PID controller is still used. So you can see those approaches as extensions of the PID controller, in the sense that the model is just used to obtain kind of a prediction of the PV that is going to be controlled by the PID controller. So you can draw things as follows. We have the PI or PID controller. This is the set point, at what enters over here is the prediction. The prediction in the future, and so on, anticipation, and this anticipation is constructed from a model, okay, and this model will use NV and it will use PV, right? So you still have a block here with SP coming in, PV coming in, and an NV coming out. It uses a model and a PID controller, so in this sense, this PID controller is kind of recycled to give you a new controller structure, and this will lead to the Smith predictor and the predictive PID controller. For in this third approach, only the model is used to obtain the controller outputs, and this is done using static or more often dynamic optimization, and this leads to internal model control that will be tackled in the last section of this course. Another approach which will not be covered in this course, is model predictive control. We'll mention it also in this last section of the course. Well, here is some motivation for process control and motivation for this course. I really believe that all engineers should have insight in control, and not only control engineers, and this will allow you to take control into the picture as soon as possible. Well, this is a survey of the actual situation, and you will see that there's really room for improvement. Control systems are often delivered without optimization and tuning, while the optimization is left for later, but later never comes, and the result is that a minority of control loops are functioning properly. I will show you some surveys that really prove this. Well, the control structures are badly constructed, and this results in badly designed PNIDs and hardly ever updated PNIDs. Control is not taken into consideration during the process design phase. These badly designed control structures come from a lack of classical process control knowledge. Key components, key ingredients of this knowledge are feed-forward, cascade, interlock management, split range, and so on. A systematic approach has to be used to combine these ingredients in order to obtain an adequate control. I really hope that this course can help. Control engineers are given very little time to concentrate on optimization and tuning. They have to keep the process running. And when finally given some time, well, there is this fear of the unknown, the fear of causing shutdowns and plant problems. You know that optimization and tuning has to be done on a running machine during production, and it's therefore sometimes difficult to find volunteers for those jobs. I hope that some of you will stand up in the future. I've told you before that most vendors offer control performance monitoring tools. You can use those tools to assess the state of all control loops using key performance indicators. So those tools simplify your job because they simply use simple production data to obtain these key performance indicators. One such tool is TuneVP by Yokogawa, and based on their analysis of control loop problems, they have found that, well, on average 15% of all control loops are in manual. So this is really indicative that there is a problem with this control loop. They have seen that 30% of these control loops have valve-related issues. We'll come back to this, and this is probably related to stiction. And that 55%, which is really a huge amount, of loops have encountered oscillatory or poor tuning. Well, here's another publication that shows that various studies indicate that anywhere from 66 to 80% of controllers are not performing as well as they should. For those of you interested in control performance management, this is a nice reference, Control Performance Management in Industrial Automation by Jelani. This is the reference that is used in the course of system identification to discuss the ARIS index, and this course is followed by the control engineer students among. This book proposes quite a number of surveys that study the control performance of loops in companies, and they give all more or less the same picture. Let us pick one out that studies the situation in North America. As you can see, well, 30% of the loops has control valves in poor condition, 60% has poor loop tuning, 85% has poor loop design, so problems with the control structure, 15% of the controls are in manual mode, and 30% of the loops are not performing according to the control object. With what we have seen before, we can certainly agree on the fact that an abnormal high quantity of control loops are badly tuned or badly designed. This means that the control structure is not adequate. Well, there is a lot of evidence for that, and the indicators that are shown here are very important as they allow you to assess the control performance of a production line. Oscillations are certainly a sign of problems with the associated control loop. It can come from bad tuning, so for instance, too much integral action, inadequate use of the derivative action, and so on. Oscillations can also come from interacting loops, so coupling effects, non-linearities in actuators, and a good candidate is stiction. We'll come back to this later in the course, but you have seen that it comes back in these surveys. Aggressive control processes with a high dead time, and also non-linearities. It could be that around one working point everything is working properly, and then you change working point and suddenly you see oscillations. This is because the process has changed, and what you can do then is, well, use scheduling, as we will see later on in the course. Another sign is alarms that are coming back on the SCADA system, and factory tuning. Factory tuning is, for instance, if you take a PID controller from the library, it might be that it comes with those parameters of here. KC is equal to 1, TI is equal to 10 seconds, and TD, derivative action, is equal to 0. We'll see later why this is chosen as factory tuning. But if you see on your faceplate that your controller has this tuning, original factory tuning, well, there is a big chance that nobody has ever looked at the tuning on that controller, and well, that it is a good candidate to start the tuning exercise. Further evidence is that there is no follow-up on tuning, and this means that the control parameters are hardly ever changed. You will find a lot of controllers in manual mode, and as indicated before, this means that the operator does not have any confidence in the associated control loop, and these controllers and the associated control structure are therefore candidates for an optimization or a review of the control structure. Very often the sampling rate is badly chosen, so for instance the sampling interval is chosen much too small. There is no filtering or inadequate filtering of PV, which means that the noise that is present on PV might find itself amplified at the output of the controller, resulting in actuator problems. And finally, you will find lots of controllers that run into the limits NVMin and NVMax. So either they are separated most of the time, or the value NV goes from NVMin to NVMax and back all the time. And this can be the sign that there is a tuning problem or that there is an actuator sizing. Section 2 on system theory is for the biggest part a review of what we have learned in previous courses. So I will not go over all the slides, and the pace will be generally high. Refer to the 2 courses that have taught you the basics, and these courses are Signals and Systems. This is a course that is also available online, and Fundamentals of Control Theory of my colleague David Huscher. Now we'll start this section 2 on system theory by this very important result that links the convolution integral and the Laplace transform. Before we go any further, we have to talk about the hypotheses that are underlying the systems that we consider. Well, this hypothesis is that the systems are linear time invariant. This means that
Nào nó qua cái video số 3 thì hơi nhiều ha. Vậy là nhóm chúng ta review lại cái video số 1, số 2 trước. Rồi sau đó thì hôm sau chúng ta sẽ đi qua cái phần video số 3, 4 ha. Ok, thôi giờ lớp chúng ta nghỉ, hẹn gặp lại vào tuần sau hả?
Cho em hỏi kìa.
Thầy nghe đây.
Vì cái bài vừa rồi là em chỉ có một người em làm thôi, thì tại em có chưa làm kịp xong cái PowerPoint đó. Em hỏi là em có xin từ sau tuần sau được không ạ?
Còn được ha.
Vì hiện tại em chỉ có một mình em làm cái bài này.
Mình
Dạ.
và các nhóm kia là 3 thành viên hết, còn mình em trong trao đổi để mà tham gia chia hai ra. Có nhóm nào làm chung với mình không? Không ha. Hôm trước là